All right, guys. So let's get started with the third one, third tutorial. Probably this would be fine, I guess. Okay, now we finished 2020, right? The May one, and we have finished 2019 November, and the spring one, 2019, the May one. Okay. Uh, all right. Probably. All right. Mm-hmm. Okay. So draw. Okay, it's drawing now. All right. So let's get started. So as I said, we will go with what 2019, the third tutorial, right? Okay. So the contents are same. Okay, guys. The instructions are the same. Multiple choice. Any what electronics are allowed? Electronic calculators, right? So each correct answer will score one, and wrong one will not be deducted, right? All right, so we'll start with 28, I guess. I marked this one before uploading to here. Yes, again, so it will start from 28. Basically, the physics starts from 28. That's the thing we have seen already, right? So let's get started. I just marked, guys, the questions only. The spring that plays Hooke's law has an unfixed length. So we have the spring, and it is what 5 centimeters. Now the load of weight 0.5 being loaded, and from the spring, the length of the spring becomes 10 centimeter now. All right, so when you load 10 or 0.15, sorry, 0.5 Newton, you had extension of what? 10 minus what? 10 minus 5, right? So 10 strength originally is 5. So extension will be 5 centimeters now. So the load is replaced with the new load, and the length of the spring becomes 15 centimeters. The spring has not passed the limit of proportionality, so it's obeying still Hooke's law. What is the weight of the load? So first of all, force equals to K times X. So here K would be what? Force over X. Well, K equals to force is when we applied 0.5 Newton, we had the extension of 5 centimeters, right? 5 centimeters. So if we do so, guys, use calculators. 0.5 simply 1 over 2 times 5, right? That would be, of course, okay. That would be, of course, 1 over 10. So 1 over 2 times 1 over 5 over 10. So 0.1, right? So 0.1 Newton per centimeter, right? All right. So, but when we apply another load, you will have the extension of, no. Another load, you will have the length 15 centimeters. So extension is 10, right? So we apply another load. So K is constant, 0.1 Newton per centimeter times, then the extension would be 10 centimeter in this case. So force equals to 1 Newton, right? So when you calculate this calculation, you will have 1 Newton. So it's C. Another question, an object X with mass 2 kilogram is moving with a speed of, all right, we have a 2 kilogram mass, so it's going with 4 meters per second. Which object has a kinetic energy of equal total object? Okay, so among these, which one they have the same kinetic energy? So kinetic energy of this guy, the object, okay, 2 kilogram object, 1 over 2, 2 times what? 4 squared, right? So uh, 4 squared would be what? This cancels. So this is 16, right? All right, so 16 joule, whatever the joule we have. So 1 over 2 times 2 mass v squared plus 16, of course. All right, let's calculate the kinetic energy, each of them. 0.5, right? So 1 over 2 times 1 over 2. Well, because 1 over 2, 0.5 times 0.5 times 16 squared, it's very huge, I guess. It's 64, right? Okay. Kinetic energy of this guy is 64 joules. The second one would be 0.5 times 1 times 8 squared. This would be, guys, 64 or 32. 64 over 2, which is 32. Kinetic energy, this is 32 joules. How about this one? 1 over 2 times 8, 4. 4 times 2 square, 4. 4 times 4, 16, right? Kinetic energy would be 16 joules. Very good. Then what? The next one, 1 over 2 times 16, 8. 8 times 1 square, 1. So kinetic energy would be what? 8 joules. So which one is same? 16. So you will have only C, right? So 29 C, of course. So for which list is the sun the original source of the energy for all geothermal resources? All, okay. Now, doesn't come from sun, doesn't come from sun. There were three that ones, right? So three sources doesn't come from the, or sun is not a resource for the three energy types: geothermal, thermal, then we had what, nuclear fusion, then tidal, right? So tidal. So all these three doesn't come. So geothermal has cancel, nuclear fusion there is cancel, hydroelectric, oil, wind. Okay, seems cancel. It's so C. It's easier if you go with this. No, doesn't sources actually. When of solid, liquid, and gas are heated equally, so we have mass of solid, liquid, and gas. They've been heated. They expanded by different amounts of, okay. Which list shows the relative order of magnitudes of the expansion starting from the state of matter that expands the least? Guys, gas will expand faster. So solid will expand slowest, right? So it will start from least would be solid, then liquid, then gas, right? So solid, liquid, gas, it's D. All right. 32, probably, oh, I call it many. So which diagram represents the wave with twice frequency? Frequency increased twice, so it becomes more dense, right? And the half amplitude. Oh, so you decrease the amplitude and increase the frequency. So it becomes like this, right? So amplitude halved. So this been cancelled already, this been cancelled already. Frequency more dense would be B, right? So 32 is going to be B, of course. 33. A student stands in front of the plane mirror on the wall. Okay, so every day we look to the mirrors. Which statement about the image of the student is not correct? The image is literally inverted. Okay. The image is smaller than the, no, it's not. Same size, okay? Same size. Same size. Mirrors give you same size actually. The image is upright, okay? The student and the image are equal distance from the mirror. It's B, guys. So it's obviously B. 34. There's a current of 3 ampere in a resistor. How much electric charge passes through the resistor in 2 minutes? Well, the definition of current would be what, guys? The rate of charge, okay? The charge per time. This would be your definition, actually. Okay, from here we can find, right? So 3 ampere equals, so we're looking for the charge, which is Coulomb, Q over time, 2 minutes, 2 times 60, right? So this would be Q equals to 2 times 6. 2 times 3, 6. 6 times 60, this would be 36, 0 Coulomb, right? Do we have such a thing? It's D. All right, 35. A sport field is next to the large school building. A student at a far from the sport field sees a groundsman hits a pole with hammer about 20 minutes. Okay. After hammer hits the pole, the student hears 2 bangs. Why does the student hears 2 bangs? So bang, it goes here, and in another one hits the wall, it comes back. Okay. This is the first one, and this is the second one. First bang caused by sound of hammer hitting pole. Okay, sound of reaching the student's left ear. Sound reaching the student's left ear. Left. What do you mean left ear? It can be right or left, right? Uh, Sound reaching student directly. Okay, this is sound of hammer hitting the ball. Sound reflected back from the school. No, not this one. Hitting the hammer. Hitting the hammer. Okay, of course you hear from the hitting of hammer. The first and second also from hammer, but the first is directly from that one. Let's read the second one. Sound reflected back from the school. This would be second one, right? So it's C, definitely. It's very easy. So yes, as I said, guys, bang. First, this one travels, guys. All right. So first, this sound first at the same time. Okay, comes. For example, here is 200 and here is 200. First, you will hear directly. Second one at the same time. It reaches here while time is here, right? So this time is t here. This is also time t when it reaches here. T1, T1. Let's see. Then it comes t whatever, for example 1 second, so 1 second come here and another second comes here, right? So it will take so t2 would be 3t, I guess, right? 3t1, let's see if they're equally what is the distance from them, but anyway, so that would be C, right? 36, in a circuit component X is placed to control the bright of the lamp. Okay, this is resistor. It controls the brightness. Ammeter. What is the component X? X is resistor, guys. Ammeter is not resistor. Fixed resistor. Fuse. No. Fuse will burn out. It's variable resistor, guys. Variable. If you remember, guys, variable resistor. It has 2-3 options, right? You will increase the amount of current manually. You will switch it. Okay. The circuit contains a power supply, a lamp, an ammeter, and NTC thermistor connected in series. The NTC thermistor is now heated. What happens to the brightness of the lamp when, and what happens to the ammeter reading? Now, so this is NTC. It's just a thermistor, okay? So it will increase that one based on the temperature. It will increase once it becomes. For example, let's say this is hot. That one, okay? If it's hot, it will switch off. But if it gets hot, okay, after some time. But what happens to the brightness of the lamp and what happens to the ammeter reading heated when NTC is heated, guys? What happens? So first, guys, so when it heated up, it will allow, guys, more current to pass, okay? It will, when it heated up, it will allow more current to pass and pass and pass, okay? So it will get bright and brighten and brighten. So the brightness will increase. Ammeter reading. So when it will allow more current, ammeter will increase too. Increase, decrease, decrease, increase, but this is decrease, increase, increase. So it's D. Logically, same, right? So logically, yes. So as it increases more and more, so it will allow more current to pass. What is the fuse? Which of the fuses are correctly placed? Don't forget, guys, fuses always located at the beginning, at the entrance, right? At the plug, okay? So this is the plug. This is neutral. So live one, this is the plug, okay? Because this is that one safety, okay? Once it's burned, high current comes, it get burned, and it will not pass inside the device. So it won't what is that? Burn the device. So fuse one only. This no, not here. One only, guys. All right. So I placed here the picture, guys. Right hand rule. It's a little bit kind of just by telling. It needed to be visualized, right? So current carrying a wire is placed between the poles P and Q of the magnet, as shown here. The direction of the current is shown. The force acting on the wire is upward direction. The force motion, okay. The force acts on wire is upward direction. What is the direction of magnetic field? Now, thumb motion. So motion means the force applied, okay? Thumb, your thumb would be motion. So your thumb looking up. All right. Now, current, the first finger would be magnetic field. Second finger would be that one, okay? The current. So it's still up. If you play with this, let me see. So force, your thumb looking up, your current going towards your screens. So it means that one. So your first finger, which is looking from P to Q, indicates magnetic field, right? So from P to Q, 39 is A. The output from the generator in a power station is connected to a transformer before electricity is sent along a transmission cable. What is transformer used? Why is a transformer used? Again, the output from the generator is, okay, generator, so the power source, okay? We have big generator, let's see. All right, so it's generator, let's see. So here's some stuff, okay. So output, okay? So output from generator. The output from generator is power station is connected, in the power station, is connected to transformer before electricity is sent along transmission cables. So this will be sent to see this, right? Here we go, here we go. All right, so why is the transformer used? To decrease the guys, we use transformers to increase voltage and decrease the current, okay? When you increase voltage and decrease the current, you will decrease the VAS a lot, okay? Voltage should be increased, the current should be decreased, okay? When you increase current, cables will heat up, they will use a lot of energy. So this the procedure done by transformers, right? By transformers. What is the purpose? To decrease the waste, okay? Waste of energy. Energy is money, guys. All right, so which one? Increase the voltage, okay? To increase voltage, CNT. Decrease, delete. Decrease the current, increase the current, decrease the current. So if current increase, guys, it would definitely have the purpose increasing voltage, actually decreasing the current, right? So 40 C. Okay, so we have finished the 3 already, and they're very easy, guys, and we can stop